There are several shortcuts to find the moment of a force about a point. Let's examine the system. This is a 36-foot high pole that is fixed to the ground. It is extended in the horizontal direction 12 feet, and at the end of that extension is applied a force 500 pounds. The sense of direction of that force is expressed in terms of these ratios. We are interested in finding the moment of this force about point A, meaning we're interested in finding the tendency to rotate of this force about point A. As discussed earlier, moment is a vector which of course has magnitude and it has direction. The magnitude of this moment is easily found if we just multiply the force with the perpendicular distance from the point you're trying to take moment about to the line of action of the force. This green dotted line is what is called the line of action of the 500-pound force. The perpendicular distance from point A, from the point you're trying to find moment about, to that line of action is this solid green distance, and I'll call that distance D. This is not a perpendicular distance, neither is this, nor this. The only one and only perpendicular distance from the point you're trying to find moment about to the line of action of the force is only this green distance. So therefore, in other words, if we can find that green distance, and if we multiply that by the force itself, 500 pounds, we'll be in good shape. How about the sense of direction? You may think of it as, how does this force want to rotate about point A? Well, it wants to rotate in a clockwise manner. I suggest that you imagine an imaginary circle which centers at the point you're trying to find moment about, which in this case is point A, and you ask yourself the question, how does the 500-pound force want to rotate around that circle about point A? Well, it wants to rotate in a clockwise manner. So I hope the magnitude is clear, and I hope that the sense of direction of the moment is clear. How does this fit with the right-hand rule? Well, the plane of F and this distance is on the xy plane. So therefore, the moment vector has to be perpendicular to that plane, which is about either the z-axis or the negative z-axis. And if you perform the cross product using the right-hand rule, your right thumb will want to point into the screen and making your forefingers want to curl in this particular direction. These two directions agree well with each other. I suggest that you don't think of the right-hand rule. The shortcut is to think of this imaginary circle and ask yourself the question, how does the force want to rotate around that circle about the point that I'm trying to find moment about? Well, in this particular case, it wants to rotate clockwise. And another element that we must find is this perpendicular distance. This is a must. If we just find that distance and we multiply it by the force itself, we'll be able to find the moment of the force about point A. I hope this is clear. The strategy is clear. Why don't we do some calculations? So let's start over. We are trying to find the moment of this force about point A. Moment is a vector which has magnitude and it has direction. The magnitude of this moment is going to be found by multiplying the force itself by the perpendicular distance from point A, the point we're trying to find moment about, to the line of action of the force. And the only one and only perpendicular distance is this distance, which we will call distance D. Okay, so our ultimate goal is to find distance D, multiply it by the 500-pound force. The sense of direction is we imagine an imaginary circle and we ask ourselves the question, how does 500 want to rotate around that circle about point A? Point A is the center of the circle. Well, it wants to rotate in a clockwise rotation. So our ultimate goal is to find distance D. Okay, why don't we take a look at some geometry. We have two triangles. This is the first one. That's the right triangle, and this is the second. And because distance D is perpendicular to the line of action of the force, therefore this second triangle is also a right triangle. We're interested in finding this distance, which I will call distance A. Well, one way to look at this is that we look at these ratios. 3 goes into 12 4 times. What that means is 4 will have to go into distance A also 4 times, and that makes distance A equal to 16 feet. Why don't we confirm this? This is 3 and this is 4. Let's find this angle. This angle is then just arctangent of 4 over 3, because we know the opposite side of that angle, we know adjacent side of that angle. By definition, tangent is opposite over adjacent, so therefore this angle is arctangent 4 over 3. Calculate that in your calculator. This comes out to be equal to 53.13 degrees. So therefore, by definition, tangent 53.13 is equal to opposite over adjacent. Opposite side is A, adjacent is 12 feet. And so therefore A is equal to 12 times tangent of 53.13. This is equal to 16 feet. Why are we interested in distance A, which is equal to 16 feet? So that we'll be able to find the hypotenuse of the bottom triangle. Well, the hypotenuse of the bottom triangle, this is of course the hypotenuse, that's the side that is opposite of the right angle. The whole height of the pole is 36 feet. From here to here is 16 feet, so therefore the hypotenuse of this bottom triangle is 20 feet. Let's look at another angle. If this is 53.13 degrees, therefore this angle is 90 minus 53.13, of course, and that's equal to 36.87 degrees, making this angle also 36.87 degrees. So we're interested in the side that is opposite to 36.87 degree angle. We know the hypotenuse, which is 20, so it's fitting that we use the definition of sine. Sine of 36.87 by definition is opposite over hypotenuse. Opposite is the distance D that we're interested in. Hypotenuse is 20. So therefore, D is equal to 20 times sine of 36.87, making D equal to 12 feet. This is wonderful. We have found the perpendicular distance from the point you're trying to take moment about to the line of action of the force. So therefore, moment about point A is a vector, and the magnitude is equal to 12 feet times 500 pounds. The sense of direction is you want to think of that imaginary circle again, and you ask yourself the question, how does that 500 want to rotate around that circle about point A? It's in the clockwise direction. So therefore, moment about A is equal to 6,000, and of course the unit is feet pounds. The sense of direction is clockwise, and of course the axis of rotation is into this screen. It's as easy as that.